Hello everybody and welcome to CCNA Scaling Networks version 6. Today we're going to be looking at Chapter 8, Introduction to Single Area OSPF. So one of the biggest advantages of OSPF is that it looks at the bandwidth as its primary metric, the actual cost of the link in bandwidth. So as you can see here, we've got two sites linking together, and if OSPF is involved, it's going to use the faster connection, those 3 T3 links. But RIP only has hop count, so it looks at the network and it thinks, well, I'm going to take the shortest path via hops, which is in this case the slowest link. So OSPF uses the metric called cost, which is all about the bandwidth. So in this scenario, OSPF is definitely a better routing protocol. So, some terminology about OSPF and how it's put together. Links. It's called Open Shortest Path first, and it's all about links. It maintains a link state database. And a link is just literally a connection, a physical connection between two devices. The state of those links, whether they're up or whether they're down. Link state routing protocol. Topology database. The interesting thing about OSPF being a link state routing protocol is that unlike distance vector, where it looks at everything from its neighbor's point of view, a link state database wants the whole topology, every single connection of every single router. All the routers must know everything. So the link state database can be quite large because it needs to know every single link in the entire topology. Areas. This first chapter we're just doing single area, and we're going to touch on multiple areas in the next module. The cost. The primary metric of OSPF is cost. Cost is the inverse of bandwidth. So the faster the link, the lower the cost. So as you can see over here on this side, we have a 10 megabit link, and that's going to cost a 10. Token ring typically used to be a 16 meg, so that's why it's got a cost of 6. And this slow link over here is representative of a 56k link, and that's 1785 is the cost. So the higher the cost, the slower the connection. So that's why in this scenario the token ring is the best path, because it's got the cheapest or the lowest cost. Routing table. All OSPF routers maintain a routing table so they can give the best routes to any destination to the router itself. And an adjacency database, exactly the same as the neighbor table in EIGRP. All the routers maintain a list of directly connected neighbors, and they form adjacencies with those neighbors. And we're going to spend a bit of time on this today. Designated router and a backup designated router. If all the routers were talking all the time, it'd be a huge fight and nothing would get done. So we have to elect a boss, someone who's in charge of a segment. And it's always good to have a backup. So we have a designated router and a backup designated router. There are 5 main packet types: hellos, database descriptors, link state requests, link state updates, and link states acknowledgements. Very similar to EIGRP, where you've got hellos and you've got requests, which are like queries, updates, and those need to be acknowledged to make sure that they get to the right place. Different states of OSPF. Down, this is not working at all. Then we've got initialization. Once we see a neighbor, we go into two-way to form our adjacency. Once the adjacency is formed, we start to exchange our data. We start the exchange, we exchange our database, we load that database, compile it up into the full topology, and once we've done that, then we're completely full. In the lab environment, you can go from two-way to full very, very quickly. But in the real world, with lots of routers and lots of networks, you could stay in exchange and loading for quite some time, 10, 15, 20 seconds, and then you go into full. The neighbors maintain their adjacency with each other with a series of hellos. And the best thing about the hellos is every single hello has the list of neighbors in that hello. So router A sends out a hello, and router B says, router A says, hello everybody, I'm router A. And then router B says, hello everybody, I'm router B, and I have one neighbor, and that neighbor is router A. So then router A knows that router B knows about it. So the next time he sends out his hello, he says, hello everybody, I'm router A, and I have a neighbor called router B. And now they both know that each other exist, and therefore they're in two-way. They can both see each other in each other's hello packets. So, once similar to EIGRP, we've got to move our database. So they wake up, he says, I've got some stuff for you, and he says, no, I'm the designated router, I'm the boss of this network, so I'm going to tell you all of my stuff, and then you're going to send me all of your stuff, we're going to acknowledge it, we're going to send up all the updates that we need, we're going to load all that into our database, compile it all together, and then we'll be in the full. So, exactly the same as EIGRP, 3 tables. The adjacency database, a list of our neighbors. The topology database, all of the connections that exist in the whole network. And then the forwarding database, which is the best paths. And this is what we give to the router so that it can route. So, routers within the same router have got 5 basic things they've got to do. They've got to find their neighbors, they've got to elect a boss, they've got to discover the networks, they've got to select the appropriate routes or the best routes, and then they have to maintain that. But if your network's fairly stable, this last maintaining thing, it might not need any work at all because nothing's changed. OSPF is one of those unique routing protocols where it only does work when there's a change. If there's no change in your network, it'll just sit back and send little tiny hello packets every few seconds, and it won't do any work. However, when it's got work to do, it can actually flood your whole network. We'll talk about that in a little while. So let's have a look at what's inside these hello packets, because that's a very important factor of the way it works. So the very first thing is the router ID. Now, unlike EIGRP, the router ID is actually critical. OSPF identifies itself based on the router ID solely. So it doesn't matter what IP addresses are on what interfaces, when you do all of your show IP OSPF commands, the identity of all of the neighbor routers, it's always going to be their router ID. And that's how they use to identify themselves. Now the timers, this is a really interesting thing. EIGRP, you just change the timers, do whatever you want, and you can break it or not break it. But OSPF actually has the timer values that are currently set inside every hello. So if you set one router with different timers from another router, they will not form an adjacency because they'll see in the hellos that there's a mismatch, and they'll just completely ignore each other and never form an adjacency. By default, every 10 seconds. Unless you've got a really slow link, and then it's every 60 seconds. The neighbors. Now this is the list of neighbors who you currently see. So the very first hello you ever send out, that'll be completely empty. And then once you identify and form adjacencies with other routers, you're going to populate that neighbor table with the router IDs of the neighbors that you have seen. Area ID, for the sake of this slide, it's always going to be 0. Because we're just doing single area. Not until the next presentation we'll talk about different areas. Now the router priority is all about the election. So if you got these, in this example we've got 4 routers. We can either let them fight amongst themselves and use the router ID as a tiebreaker for who's the biggest, baddest router, who's going to be the boss, or we can just set one of them with a priority. So by default the priority is 1, so we just set one of the routers we like. The most powerful router, best CPU, best RAM, we say, right, your priority 10. And it'll always win. It'll always win the election. Because the BDR election is who's the boss and who's the backup boss. There's also authentication, same as ERGRP. We're going to talk about authentication, and we don't need to talk about stub at this stage. And different types of networks. So broadcast multi-access, standard Ethernet network. Point-to-point, standard serial network. Non-broadcast multi-access, frame relay is pretty much the standard for that one. Thing to note here that the BDR election will only take place on a broadcast multi-access network. It does not take place on a point-to-point because it's just a point-to-point. There's no point electing a boss and a backup boss because both ends need to know who's who. And in non-broadcast multi-access, you have to do a little trick to get the BDR election to take place. So, router A down here has got a problem. One of his networks has gone down. So he sends an update to the designated router, say, I've got a problem with the network. Just animate that again. So, link goes down on router A, we send a link state update to the DR. Notice that this, and the DR acknowledges that. Notice that this is a multicast and it's 224.0.0.6. So it sends a multicast address on 224.0.0.6, and that is a multicast to all designated routers on this network. Then the designated router has a responsibility to send the updates to routers B and C, all the other routers. This message from the DR to everyone else is sent on 220.0.0.5. That's very important because there are two multicast addresses that OSPF uses. And in this example, router B has a responsibility of forwarding that update on to the next guy. Alright, so let's have a look at how we actually configure OSPF. Now, loopbacks are very useful tools. You don't have to use them if you don't want to, but they can be used for many things. In OSPF, they can be used for helping you identify your router. You can use them as for testing or development or all sorts of things. So loopbacks, we'll talk about loopbacks a little bit further on. But the interesting thing to note here is that there is no class system or automatic summarization or any of that sort of stuff with OSPF. OSPF must have a mask. There is nothing implied with OSPF. You must have it in your network statement. You must have the IP address, network, and the mask. If you try and leave the mask out, it will not accept it. Also notice that there's a wildcard mask. So the default subnet mask for this will be 10.1.2.0, 255.255.250. So with the inverse mask, you just completely mirror image it. So 255.255.250 is mirrored to 0.0.0.255. And the area ID. Even though we're only doing single area in this first module, you must have area 0. That single area that we're working in is area 0, and the slang term for that is the backbone area. Interface. We're in interface mode now, so put an IP address 10.1.2.1 mask. Now, IP OSPF priority 3, this is purely for the BDR election. We're using the priority command to manipulate that election. And exactly the same as exactly the same as ERGRP, we're using the bandwidth command to trick the routing protocol into the speed of this network. Notice here too that this priority command is on the interface mode. So if this router's got 5 interfaces, you can say one interface is going to be the DR, a different interface is going to be the BDR, and a different interface he can not be the DR or the BDR. It's completely configurable. Useful commands: show IP OSPF, show IP OSPF interface, show IP OSPF neighbors, show IP OSPF database. And now, I said we'd be talking a lot about the BDR election, so let's have a look at it. OSPFs must perform an election on all multi-access networks. So you can see that the very left-hand network, there's been an election, but there's only one router there, only one link, so therefore that's the DR. In the center, it's an Ethernet segment, so there's been an election. And on the right-hand side, it's a point-to-point. So there's not multi-access, so we don't need an election. Both B and C will just assume the designated router role. but everywhere there's a broadcast multi-access or Ethernet section, there's going to be a BDR election. Alright, so how do we manipulate that election? How do we make that election do what we want? By default, priority is the #1 thing. So no matter what you do with anything, whoever has been set with the highest priority is going to win the election and become the designated router. And the router with the second highest priority will become the backup designated router. So typically, if you've got 3 or 4 routers that can all see each other on an Ethernet segment, you pick one and you give it a priority of 20, and then you pick the one you want to be the backup and you give it a priority of 10, and that's it, you're done. Everything works. However, fresh out of the box, all the routers have the same priority. So if no priority is set, they've all got the same priority of 1, then the router ID becomes the most important factor for who becomes a designated router. Now, the router ID can be generated by programming it inside the OSPF process. It will look at all the loopbacks you've got, if you've got any loopbacks, and it will take the highest IP address from any loopback, and if there are no loopbacks configured, it would use the highest IP address on any active interface. So the router ID can be programmed inside the routing process. It takes the highest address of any loopback if configured. If no loopback is configured, it is the highest IP address on any active interface on that router. So, if you want to find out what is going on your interface, show IP OSPF interface and the interface number. And I've already talked about why the significance of the priority command is, because it is all about what. So let's see who was paying attention on the previous slide. We've got 4 routers. We have got 1, 2, 3, 4, 5, 6 Ethernet segments. So we don't need to know what is happening on this segment, and this segment, because there's going to be election, and this router is going to be the designated router for this segment. This router is going to be the designated router for this segment. This router is going to be the designated router for this segment. But we've got 1, 2, 3 places where an election can occur. So we're just going to pause for a few seconds, and you can pause the video if you want and get a piece of scrap paper. And I want you to scribble down these 3 links and say, so we've got top and left, top and bottom, top and right. Who's going to be the designated router on this link? Who's going to be the designated router on this link? Who's going to be the designated router on this link? Pause the video and come back in 5 seconds after you've written those down. Alright, so hopefully you've spent a bit of time writing that down, and let's see if you were right. Now, the only thing that matters is the router IDs. The router ID here and the router ID here. A lot of you are probably looking at this saying, well, hang on a minute, 10.1.3.2 and 10.1.3.1, well, which one of these is higher? Well, hopefully you weren't doing that, because then I'd have to go back to the previous slide and say what is the way the router ID is generated. Remember that the router ID is generated by the highest IP address on any active interface. So let's have a look at some router IDs. You all thought that the left-hand router ID was 10.1.3.1, didn't you? It's not. It's the highest IP address on any active interface. So what is the router ID of the top router? Now when you look at it, who's going to win the election? It's obvious, because 192.1.2.1 is higher than 10.1.3.2. 10.1.3.2 is higher than 10.1.2.2, and 172.1.1.2 is higher than 10.1.3.2. You got to remember that the router ID is generated by the highest IP address on any active interface. Neighbor adjacencies must be formed before they can do all this lovely work. Link state advertisements are used to learn the topology, and the link state advertisers are multicasts. All the routers in that same area, and that's a problem. The primary metric of OSPF is cost. It's all about the cost. And cost is the inverse of bandwidth. So 10 to the power of 8 divided by bandwidth is a number. Now, when the guys were designing OSPF, 10 megabit Ethernet was brand new, and it was blowing everyone's minds. They thought, 10 meg, my goodness, what is going on? This is ridiculous. However, as the years have gone on, we've gone to 100 meg, we've gone to gigabit, we've gone to 10 gig, we've gone to 40 gig, we've gone to 100 gig. So the math breaks down, because OSPF can't tell the difference between a gigabit link and a 10 gigabit link. So we've got this lovely command that we need to have. You can manually set the cost, but you got to do it everywhere, because you can't have two routers thinking that the same link has a different cost. But an easier way to do it is just to move that mathematical calculation of 10 to the power of 8 divided by bandwidth, add a few more zeros on the end. So rather than say 10 to the power of 8 divided by bandwidth, make it 10 to the power of 16 divided by bandwidth. And therefore, 100 gig might have a cost of 10. 10 gig will have a cost of 100. 1 gig will have a cost of 1,000. 100 meg will have a cost of 10,000, and 10 meg will have a cost of 100,000. And that way you just have this one command, and all of the interfaces will figure it out themselves. So I strongly recommend you just write in your journals and put in every lab auto cost reference bandwidth, and make it, so if you just put 100, that's what the default, 100 meg. So I would make that, 10,000, and therefore that would be 10 gig. Or you can make it 100,000 if you want, depending on how granular and how future-proofing you're trying to make it. Remember that cost is all about money. So if you've got to get from A to B, do you want to pay lots of money to get there, or save your money and do it on the cheap? That's what OSPF wants to do. It wants to get there on the lowest cost. So we don't spend a lot of time on frame relay, unfortunately. I love frame relay and I really miss it. But in the real world, you may well come across frame relay. Now, frame relay by default does not support broadcast, and in fact, it doesn't even support multicasts. So what we have to do on our non-broadcast multi-access is that those hellos are going to struggle to find the neighbors. So what we do is we say, you know what? Don't send out multicasts looking for neighbors. Send out a unicast, because this is the IP address of your neighbor, and therefore you'll be able to find you'll be able to find your neighbor, and everything will be fine. So this is the command to actually set up frame relay. This is all frame relay, standard frame relay stuff. But this is a trick to say, all right, OSPF, don't send multicasts to form an adjacency. Send a unicast to 10.1.1.2, because that's your neighbor. Differences between OSPF version 2 and OSPF version 3. Now, thankfully, these differences and similarities are exactly the same as the similarities and differences with EIGRP. Have a look at your 224005 and 224006. Thankfully, for IPv6 or OSPF v3, FF02:5 and FF02:6. So you don't have to memorize the IPv6 numbers, because it's the same. EIGRP is the same, RIP is the same, OSPF is the same. So whatever multicast address they use, the IPv6 version is exactly the same number at the end. Very nice. And exactly the same as EIGRP, OSPF IPv4 has network statements. OSPF version 3 for IPv6, you put the command in the interface mode. And as far as authentication goes, you can set up manually authentication for IPv4, but in IPv6, the IPv6 can take care of the authentication for you, so you don't have to worry about it. So let's have a look at how we configure version 6. Exactly the same as the ERGRP. We go in, we set up our IPv6 unicast routing. If you forget that, nothing works. We set up our OSPF. Now this number is just a reference number, an instance number I should say. We set up the router ID. Always got to have a router ID because you have to set a router ID manually. Because how does OSPF get its router ID? It leeches it from any active interface. But what if you don't have any IPv4 active interfaces? Then you have to set it manually. And of course, a favorite command, autocost reference bandwidth 10,000. So we set up our IPv6 exactly as normal, and now we say IPv6 OSPF 1, which links it to this one here, area 0, done. So to recap, IPv4, network statements. IPv6, inside the interface. All these commands are exactly the same. Show IPv6 interface brief, show IPv6 protocols, show IPv6 OSPF neighbors, show IPv6 route. And that's the end. Thank you very much, and we'll see you in the next one.